Okay, I'm live, folks, and you are again. I hope I'm not interrupted. If I am, I'm going to have to discontinue this broadcast, but we're live. And once again, we are looking at the results of our last video. We did an experiment where we had an apparatus uh, where we inflated a balloon and measured the difference in the buoyant force that this inflated balloon introduced into our weight determination on the scale. The weight of the apparatus went down. We took the difference between the original and final values, and that was actually equal to the weight of the buoyant force acting upward. And according to Archimedes, that's the same as the quantity of air it would take, the quantity of air that was pushed away in inflating the balloon, or in other words, the amount of air that it would take to fill the volume of the balloon. And if we divide the weight, or actually mass, by that volume, we'll actually get the density of the air. And this was our way of determining it. Well, we took down some readings. I'm going to go over what we did. The initial weight of the balloon and the 152.5 grams, and the weight registered on the scale after the balloon had inflated was 346.1 grams. In other words, a buoyant force was introduced by the inflation of the balloon. When we subtract one from the other, we get 6.4 grams, which was the actual, shall we say, measure of the buoyant force. I know some of you are going to say, well, that's a mass figure and that's not force. But for now, we're just going to look at it as a weight, if you don't mind. 6.4 grams. Now all we need to do is find how much of the air was displaced by inflating the balloon, and that's really the volume of the balloon itself. I used two methods to determine the volume of the balloon. One was by dunking the inflated balloon in a pot of water and displacing however much water would be displaced. I filled the pot up to this pot. I filled it up to the brim, and then I dunked the balloon in it. The water overflowed. I caught the water in this wider pan here, and bit by bit, because if I submerged the entire balloon, it would fill too much of this pot. But bit by bit, I did it, and then put the overflow in different pots and collected it, and then measured it with this measuring cup here and with this graduated cylinder for smaller amounts. Okay, so using that method, we arrived at a figure of 4.563 liters. Now, the problem with that method is that when you dunk the balloon, you actually put pressure. The water pressure kind of shrinks the balloon, so you're going to get a lower figure from that. Plus all the splashing around. I'm sure some of the water splashed over the sides, etc. It's something that has to be done pretty carefully. At any rate, there were two other methods that I used to, I should say one other method that I used, but I had to take two measurements. We know that the balloon is not a complete sphere. The balloon is a kind of tear-shaped upside down tear-shaped object. So we took one circumference based on sort of the waist, the largest waist measurement of that teardrop shape. And then we took another measure of the circumference going along the longer up and down, um, up the other way, the longest, shall we say, using the longest circumference. And and then we determined the volumes, assuming that these would be spheres. And the actual volume of this teardrop shape is somewhere in between the smallest and the largest that we got. And the smallest came out to be 4.588 liters. And using that as I don't have it marked here. Using that, using that calculation, we arrived at a density of 1.13 grams per liter. And then we then did the larger volume. Actually, I should mention that the original circumference was 25.5 inches, which we converted to meters. And the large one was 27.5, so it was a larger circumference. And for the larger circumference, we got a volume of 5.755 liters, and that gave us a density of, I think it's wrong again, 1.39. Okay, with the smaller volume, our density was actually 1.39, and with the larger volume, our density was naturally less, at 1.13. Now, if you average these two together, and I'm not saying that this is statistically the most accurate way to treat these figures, but let's say we just take the average of these two high and low estimates, we would get about 1.26 grams per liter as the density of the air. Let's remember that we are at a certain elevation with a certain barometric pressure, and I'm, roughly it was room temperature, but I didn't have a thermometer in here. So 1.26 is a rough estimate based on our experimental results, which were a high end and a low end. And if we compare that with an internet source, at least one reputable internet source, I use Vedantu.com. They come in for room temperature and what they call normal atmospheric pressure, whatever that might mean. They come in at 1.289. We come in at 1.26. I'm just saying that basically 1.26 grams per liter, just to show you that our estimate is roughly in line with others. As I said, case by case, point by point, wherever you are, we have a certain elevation here. The barometric pressure may be less or more, etc. But it does show you that we are in the ballpark in terms of what we should come in at. So our experiment, with all the different ways in which we use to get the figures, our experiment worked out. I just want to say that we measured the circumference of the balloon using this paper towel, and I marked the lower, and the upper measures of the circumferences. One around, the lower one being around the waist of the teardrop-shaped balloon, and the larger one being, from top to bottom. And this is how we did that. We just wrapped the paper towel around it and marked the measurement there. So you can use all different kinds of stuff around the house to configure this. We eventually use this tape measure to actually get the amount in inches and then convert it from inches to centimeters at 2.54 centimeters per inch, and then dividing that by 100, we've got meters. Okay, so we now know that the air, at least in this room, is about 1.26 grams per liter. Air does have a weight, and that's about what it is. I want to thank everybody. This was somewhat instructive. My button keeps unbuttoning here, but these are my work clothes. This is a work session, so like I said, for listening, and who knows what our next experiment will be. As I said, we can do some very interesting things with this scale, and we show off.